Okay, this is the Module F data manipulation video, and let's see if we can get this thing going from the beginning. So the activities are pretty standard. What you've done is you went on D2L and you've downloaded the PowerPoint, which allows you to click on a link and watch the lecture video. You're going to follow some links. You're going to stop it when prompted and watch some additional linked videos. You'll fill out the lecture video worksheet and turn a completed worksheet in. The outcomes for Module F are as follows. How does a move instruction work? How do compare instructions work? Explain how manipulation instructions are similar to outputs. Explain how compare instructions are similar to inputs. How can manipulation instructions be used to generate recipe programs? What is a practical example of an up-down counter program? Before we do that, we'll take a quick review of timers and counters. So counters in the SLC 500 have memory location C5. There's 256 counters available from C5:0 up to 255. And then the extensions on them are the ones that we normally use was the done bit. So we've used C5:0.dn. We used a lot of the done bits. CTU counts up. Preset meets the accumulation. The done bit comes true. And then countdown counts down. We compared these to pneumatic, or excuse me, we compared these to rotational or mechanical counters when they count up or count down and then they become done. The counters are retentive, which means that they need a reset. So if you lose power to the CPU or something like that, when you turn it back on, the counter will remember the accumulation number. Reset, RES will reset it. Timers are memory location T4, 256 timers available. It's T40. The different type of timers were TON, RTO, and TOF. And so TON and RTO are on delay timers, and we took a look at pneumatic timers from ELTE131 and made comparisons. And the TOF is an off delay, and we made a comparison to the 131 off delay timers. The bits that we used a lot were the EN.EN, so T4:0.en is the instantaneous contacts. The TT is true during timing, and this is a combination of the EN and then a normally closed time contact in series. So the TT is kind of a nice addition here, and we learned about that. And then the DN, so when the accumulation hits the preset, the timer becomes done. Take a look at these two circuits here to take a look at some of the idiosyncrasies of scanning with regards to timers. Okay, wanted to talk about the timer combination at the back to be sure that you understood how it was working. So if we take a look here, we have PB4, which is going to advance the counter. And we had, I guess, 4 times here. So when we push the button and it goes false to true, 1, false to true, false to true, false to true, 4 times. The accumulation goes 1, 2, 3, 4. And so when the accumulation hits the preset, the counter becomes done. And it's retentive. It stays at that count until it's reset. And I don't have a reset in this program, but you would need a reset. So the counter 5 becomes done. So this becomes true. This is a closed, and this is closed to start with. And so this is going to turn the light on. Oh, I see an issue here. This should say, I think my total blink. This should be my blink counter, my C51, by the way. So disregard that. So we have this getting done, and then this is true, and this is true, because this is associated with this counter. And the light comes on. Okay, so that counter turned the light on, and that counter also starts a timer. So the timer goes 1001, 1002, because it's 200 times 0.01 is 2 seconds. 2 seconds, so then after the counter, this goes 2 seconds, and it closes this, which starts another timer. This is called a cascading timer. Timer starts a timer. And then so what this timer does is it is going to time to 1 second, and then it is going to open up the rung to the first timer. Well, if you open up the rung to the first timer, it resets, causing this to go false, causing this to reset. So if you want to think about it, the purpose of the first timer is to start the second timer, and the purpose of the second timer is to reset the first timer, and then that just resets itself. Okay, and so what are we using these timers for? T46 right here, the blink timer, T46.dn. So every time this times out and then resets and times out and resets, this contact keeps coming true, then false, and true, then false, and true, then false, and that gives us our blinking light. And then here we had the reset timer. I use the second one here. I use the second timer to advance the cycle. I didn't use the first one because the cycle involves the first timer completing and then the second timer completing. Both timers cascaded together represents a complete cycle. So I used the second cycle done bit to advance the counter. And then when that complete cycles 1, 2, 3 times, it becomes done. And this where there should be C5 done, and then that would turn the light off, and the light would no longer be available for blink until this got reset. So this would need a reset. There was a homework and quiz, so be sure you got the correct answers for that. The week 6 topics are up-down counters, move instructions, and data compare instructions. So an up-down counter is pretty cool. Basically what we were doing is we're going to have a counter up and a counter down. And this is another one of those cases where we address the same. So we put C5:1 and C5:1. So we've taken a counter and we've addressed it with the same address. Now normally we don't address things with the same address. The one things that we've learned are our latching instructions, our counter and our resets, and our time and our resets. But if you do an up-down counter, you make it C5:1 and C5:1. You address the same counter. So what is going on with logic? You give it a preset. So when you enter this switch here and this becomes true, it will go up and this will increment 1. And it will also indicate 1 here because they're the same counter. So if I close again 2, 3, 4, this would go 2, 3, 4, and this would go 2, 3, 4. It would acclimate. And it would show on both of these counters because they're the same address. If I hit the exit switch, 1, 2, 3, it would go from 4 to 3 to 2 to 1, and so would this one, 4 to 3 to 2 to 1. So one switch causes the counter to go up, and another switch causes it to go down because we're using the same counter with a counter up and a counter down. And this is an up-down counter, and it might be like in a parking lot where cars come in, and then they make a switch to say that the parking lot's filling up. And maybe it gets to 150, you have it done, and say that the parking lot is full. Well, if somebody leaves and clicks this, the count would go from 150 to 149, and then it would no longer be done, and the lot full light would go off. So that's a good example of an up-down counter. Data manipulation instructions allow data stored in the controller's memory to be operated within the control program. Well, that sounds complicated. We'll have to explore what this means a little bit. When we say data, we're talking about ones and zeros. Okay? Typically, we're talking about a register or a word. So this register word right here is a 16-bit word. There's 16 ones and zeros, this register word. There's double words that have 32, but we're going to stick with just a word here, or a 16-bit register. Now these ones and zeros mean something to the CPU and to the program that we're working on. Okay, so we get ones and zeros of this word, and when we group them together, one word, 2 words, 3 words, 4, it's kind of like you're reading a book here. That's called a file. Okay, so this is the register, the word data, and this is when we're talking about that we're manipulating. So as a smaller note, we have each one of these ones and zeros is called a binary bit, and it's binary because it can only be 2 states, 0 or 1. So this 16-bit register word right here is made up of individuals, and then you group the words into a file or a table, and then this file or table means something to your PLC program and to your CPU. The data manipulation instructions are output instructions. So these need to be dragged in similar to timers and counters where they go on the right side of the logic, and they're in here under move logical. Okay, so this is where you're going to find the move masks and or XORs. The one that we're going to be working with is going to be the move command. Okay, there's other ones here, file miscellaneous with copy, and then we'll do our compare ones is what we're going to be. So this lab will use these ones here, and mostly the move command right here. But here's some other options here that we go into in the advanced PLC class. So data transfer involves the transfer of the contents of one word or register to another. So we already know what a word is. It has 16 bits in it. So let's see what that means. So let's say we had a register, and here's our register of these zeros and ones and zeros and ones. This means something. We don't need to know what it means right now, but it means something. So in this case it says original data are in register N30 and N20. So N20 and N30. And so let's say we're going to do a transfer. It has occurred. So we want to transfer the information in N30 up to N20 because we want to move this data around. And we'll see why in a minute. So basically, the data in N30, it could remain there and it could be duplicated. And then it overwrites the data in N20. And so now N20 matches N30. So we have all these N20, 21, 22, 23, 28. These can contain all ones and zeros that we keep moving around and modifying and such to get the desired output from the PLC that we want based on ones and zeros. We're basically moving these words around. Okay, and N for a SLC 500 is where you store word data. N7, just like counters were C5, timers were T4, bits were B3. If we just have a word, some data, we can store those in these locations, N7. So the move instruction is used to copy the value of one register to another. Okay, so the move is going to be right here under the move, and it's going to take the source and it's going to move it to the destination. Okay, so the source could be an N value, a register, or it could just be a number like 300 or 500, and it's going to move it to a destination, which could be like an N register, or it could be something like a timer or a counter preset, and that's what we're doing today. Let's take a look at this one. So for some reason, when this switch is made, and this becomes true, we're going to move N30 into N20. So all the ones and zeros here get moved up to N20, where all the ones and zeros there. And we have to figure out why we would want to move those ones and zeros, or why we would want to move something. Okay. So move instructions to change the preset time of a timer. Here's a good one. So we have a push button. Let's say I hold the push button down. This timer is going to time, but we need to put a preset in here, like we want to put 5 seconds or 10 seconds or 20 seconds or something like that, right? So we have a selector switch, and so it's either going to be true or false or true, because it's going to select one or the other, and we've used it once. So if for some reason it's selected one way and rung 2 is true, well then this will move 10. Looks like we're pulling it out of N7-1. We don't need to necessarily pull it out of N7. We could have actually just put 10 in there, by the way. And it moves 10 into the T4-1 preset, which is right here. So if this is true, we've made ourselves a 10-second timer. If we click the switch, then this goes false and this goes true. And what it does is it moves a value of 5 into the preset. And so now we've got a timer that's a 5-second timer. So we might alternate between wanting a 10-second timer or a 5-second timer, so that when it became done, it would turn on a light. Okay, so that's a lot of what we're doing today, is moving things like that. So here we have move instructions to change the preset of a counter. So if this LS goes click, 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 this is going to count up, and accumulation is going to go up. What do we want to accumulate it to? Well, depending on if we have A, B, or C, if A is true, it is going to move 300 into the preset, and we would have to click this limit switch 300 times for the done bit to come true and the parts to be full. If we click number B, let's say we got an order for that we only want 175 parts in the box, let's say, so we would activate B, and it would move 175, and then the conveyor would put 175 parts, and such. Or C, if we only had a order for 50, we would put 50 into the preset, and now we have a 50 count counter. So depending on what the customer ordered, A 300, B 175, C 50, we could have something that counted the number of parts when it hit the limit switch, and then we'd get a full light. Here's some move example on video. Watch that video and take a look and be sure you understand. Data compare instructions are input instructions used to compare numerical values. Okay, let's see what that means. So the logics are what you're similar to: equal to, not equal to, a number that's less than a different number or greater than a different number. These hopefully make sense to you, where we're just comparing two values. Let's say 2 is less than 3, okay? And if that occurs, 2 is less than 3, then we want our logic to be true. Or we want greater than is 5 is greater than 2, then we would want our logic to become true, okay? So the compare instructions are under compare here, and there's limit test, mass comparison for equal. We're not necessarily using these two today. You might use limit, but you can do a lot of different things with these here. Equal, test whether they're equal, not equal. These should be self-explanatory. Less than, greater than, less than or equal, or greater than or equal. So those are your different compare commands that we have available. So the equal instruction compares the value of source A to source B. So let's say we have a timer that's timing, and it's timing 1 second, 2 seconds, because that's the accumulation, 3 seconds, 4 seconds, 5 seconds. If for some reason in N740 we had a value of, let's say, 10, we wanted something to occur when the timer was at 10 seconds. So this would keep accumulating up to 10 seconds, and for a brief moment, when the timer, the accumulated value of the timer that we've got in here, is equal to 10, this light would be on. And then the timer would go to 11. It's no longer equal to 10, and the light would go off. Okay? So why did we put 10 in N740? Well, we could have just put 10 in here, but it looks like they were trying to pull some data from the register file. So that could be an option. You could just be putting the value in there. Not equal to. So here's one where once again they're showing that they're pulling it from N7, but really it might just be 30 if you were comparing 30 to 25. So if it was not equal to, the light would come on. So in this case it's not equal, but if for some reason the source was like a counter or a timer or something like that, and that this was changing, from 0 all the way up, for a brief moment 25 would be equal to 25 and the light would go off, but in all other cases it would not be equal. So this source could be like a timer or a counter accumulation value, or it could be a register. It could be a variety of different things where you're getting your source from. Here is a numbers where they just put the values in. There's no N7 file. So we're saying the timer, this timer's, we turned it up. Somewhere in the program there's a timer that we've turned on, and the timer is running 1, 2, 3, 4, etc. and the timer's timing, and it's going to time for 200 seconds, and the light is not going to be on. But once it hits 201, because we're looking to be greater than 200, once we hit 201, the light will come on. That's greater than. Here's less than. Once again, it looks like they're using a counter, and then they're just comparing it to 350. So they're not using the N7 register file. They're just flat out, there's a counter in the program somewhere. They're taking the accumulation of it. So every time you advance the counter, 1, 2, 3, 4, that's all less than 350. So the pilot light is on. But finally, after a while, when the counter gets to 351, 352, 353, this is no longer true, so the pilot light won't be on. Less than. Greater than or equal to. Once again, 100 is greater than or equal to this. Turn the light on. If it's not, the light won't be on. Less than or equal to. Same thing. Looks like we've got a counter that's accumulating. If it's less than, So if it's 455, it's true. 456, it's true. 457, it's true because it's less than or equal to. But at 458, 458 is more than 457, so the light would change. Here's a limit test. So you can put the item that you want to test here in the middle. So it could be an integer, it could be a counter accumulation or timer accumulation, and then you could put a limit between the two of, let's say you're doing a timer accumulation, so between 2 seconds and 5 seconds. And you would put your timer in here, and between 2 and 5, this would be true. So here's an example of 25 to 50, and so it looks like at 48 it's true, because between 25 and 50 it's true, and on the high and the low side it's false. Limit test. This is another one where you're looking at the outsides. It's just very similar. You're looking for what is true on the outsides compared to what the test is, and it would be false in the middle. Okay, don't use the limit test in this way very often, but it could be available to you. Here's watch some example videos of using data compare. So let's take a look at doing some circuits here. So we have a hardwired circuit over here. So we hit start, we have a control relay latching itself on. So if we were going to make ladder logic out of this, we could do a timer, and it looks like it's a cascading timer. This timer gets done, starts this timer. This timer gets done, starts this timer. This timer gets done, you know, and executes this run. So we could do cascading timers of timer starting a timer, starting a timer, and then these other items could be turning on. We could also use it, it looks like, with a single timer. So we could say that, you know, this is 5 seconds, and then 5 seconds, and then 5 seconds. So they add, this timer gets done, and 5 seconds later this one starts, and 5 seconds later this one starts, so, and 5 seconds later this. So it's all cascading. 5 plus 5 plus 5 is 10. So if we compare it to ladder logic, what we do is we'd have a start, and I guess they're using the solenoid to create its own memory. So the solenoid comes on, and that satisfies this here. The solenoid turns on a timer. That's the first timer here, and that's our only timer. We're not going to do these other two timers because we're just going to say this first timer after 5 seconds turns on the solenoid. So let's see. Timer 4-1 accumulation. So the timer becomes true. It starts 1, 2, 3, 4, 5. And when it's greater than this, that means that was normally open time closed at 5 seconds. Solenoid B came on. It did. So this is going to be greater. But this timer keeps going. 6, 7, 8, 9, 10. When it gets to 10 here, then, you know, this was 5 plus 5. This closes, so at 10, solenoid C comes on. We didn't have a timer starting a timer. We're just using a single timer. And we're picking off when it's 5, 10, 15. So this comes on. And then finally, this timer started the third timer. And then this was done totally at 15 seconds. Well, what they did here was they made the preset 15. So 5, 10. After 15, this became done, and solenoid D came on. So this is one way to do it. You could certainly have had a timer starting a timer, timer starting a timer, timer getting done. This might be a cleaner way to do it, using greater than or equal to's. Here's an equal instruction. Switch 1 starts a timer. Time base is 1. So it's going to try and get to 20. So it's going to 1, 2, 3, 4, 5. As it's going up, we have this accumulation is changing. We just pulled it from here. 1, 2, 3, 4. At 5, it's equal to it. So we will latch the light on. So now this is retentive. As it moves to 6, the rung wants to go false, and it will, but because we've latched the light on, it stays on. So it goes 6, 7, 8, 9, 10, and it keeps going all the way until it gets to 15, and when it gets to 15, the light goes off. So in this case, the light is on when the timer is between 10 and 15, and the timer keeps going 16, 17, 18, 19, 20, and it's done timing. But between 5 and 15, it looks like this pilot light would be on. Here's a counter. Sensor makes a counter. 1, 2, 3, 4, 5. I'll get all the way up to 50. Okay. Here's the accumulation value. Well, if the accumulation is less than 20, we've got a solenoid that's on. So it looks like the solenoid is a diverter. So for the first 20 parts, because it's got a sensor here that's counting the parts, for the first 20 parts, it looks like the solenoid is on because the accumulation is less than 20. But after it hits 21, looks like it's no longer on, and maybe spring returns this, and then it sends parts another way for a total of 50. So after we hit 50, it gets done and it resets. So it looks like we end up with 20 parts down one way and 30 parts down the other. We have a concept of state manager that you're going to need to take a look at. So a state manager the premises of this is that sometimes it's nice to use the prior rung completion, or the memory from the prior rung, in order to start the next rung. So in this case, there's a couple of things going on. So in this rung, for example, it looks like we have something that's going to get extended and hit a limit switch. Okay, and then that is going to create a memory internal within bit, because this memory is latched itself on. So even after we take the part away from the limit switch, then this bit extend is true. Okay, so because this sequence happened, that starts the next sequence here, which would be the extend timer true, and then that timer would start timing. Okay, now why is this important? What happens if we just use the extend limit switch here to start this timer instead of this bit that's connected here? Well, if we remove the part from the limit switch, the timer would reset. But the way that we've got it here, we have the extend limit switch created memory. So even after we remove the part from the limit switch, the memory remains, and so this remains true, and so the timer continues to time even if we take the part from the limit switch. Okay, and so here's another example of a state manager where we have the extend timer true, starting a timer. Here's a cascading timer. So this timer starts another timer, supposedly, because this timer is getting done. But in this case, we might have a retract limit switch that is already made. Okay, so we didn't have this done bit here. This retract limit switch would automatically start the timer. Maybe we didn't want this timer to start until the timer before it was done. So we have the state manager of this timer getting true, and then this enables the rung. So now the limit switch is what controls this timer. But the limit switch is only active if the rung before it has finished, because we've tied it in here with the done bit. So that's kind of a state manager, is that something from the prior rung is initiating the logic on the second rung, and then there can be contacts on the rung, but they're not going to work because something needs to be closed to enable that rung. So tonight's class, there's an example of a state manager in the lab. You want to take a study it, and it will help you with your lab. So there's a master control relay handout you want to take a look at on this connection video right here. So watch this of how to connect the master control relay. You want to verify the wording of the group lab with the instructor to be sure that you understand what the group lab is. You'll be working with a group, and you're going to want to divide and consult on this task at the very end of the lab for a maximum team grade. Okay. So there's going to be a quiz for this unit and a lab.